Hi guys, this is Dr. Bay, and here's Bugsy, and today we're going to go over electrophilic aromatic substitutions or EAS reactions. So stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Electrophilic aromatic substitutions or EAS reactions are where one of the aromatic hydrogen atoms are replaced by an electrophile. There are a variety of new groups that can be installed on an aromatic ring, such as halides, sulfonic acid groups, nitrate groups, alkyl groups, and even acyl groups or carbonyls. The general scheme of an EAS reaction starts with a benzene ring. One of the pi bonds or double bonds in a benzene acts as a nucleophile and attacks the electrophile, and then the leaving group breaks off. The electrophile then attaches to a carbon atom on the ring, and a carbocation forms at the other end of the original alkene carbon, and this intermediate is called a sigma complex. Then a nucleophile deprotonates a hydrogen atom, and the alkene is reformed to get a newly substituted benzene ring product. Now let's get into the details of each of the 5 EAS reactions we will cover in this video. The first EAS reaction is aromatic halogenation, where E can either be chlorine or bromine in the presence of a Lewis acid catalyst made of either aluminum or iron. The mechanism starts with first forming the electrophile. In this example, we're going to use FeBr3 as our Lewis acid catalyst. One of the bromine atoms in Br2 attacks iron to then form our electrophile. Then in the second part, we will add our electrophile to the benzene ring. One of the pi bonds in benzene attacks the bromine atom at the end of the complex, and then the Br-Br bond breaks off. This forms a positively charged intermediate or a sigma complex, sometimes it's even called an rhenium ion. Notice that the sigma complex is not aromatic because it is not fully conjugated due to the lack of p orbitals at that sp3 hybridized carbon atom. Then in the next step, the sigma complex is deprotonated, which restores aromaticity in the product. The next EAS reaction is called sulfonation, where E is a sulfonic acid group. Fuming sulfuric acid is a mixture of H2SO4 and SO3 gas, so you can either write out fuming sulfuric acid, or you could write out the two separate reagents as H2SO4 and SO3. The mechanism starts with sulfur trioxide, or SO3, acting as an electrophile. One of the pi bonds in benzene attacks the sulfur atom in SO3, and one of the SO double bonds breaks to form a new lone pair on oxygen. Then an intermediate sigma complex is formed. O- gets protonated by hydrogen and restores aromaticity in the product. The next EAS reaction is called nitration, where E is a nitrate group. The mechanism starts by first forming the electrophile NO2+. Nitric acid acts as a base to accept a proton from sulfuric acid. Then one of the lone pairs on O- pushes down to form an ON double bond, which causes water to break off. The resulting nitronium ion acts as an electrophile. Then in the second part, we're going to add the nitronium ion to the benzene ring. One of the pi bonds in benzene attacks the nitrogen in NO2+, causing one of the pi bonds to form a new lone pair on oxygen. Then water deprotonates a hydrogen atom in the sigma complex, and aromaticity is restored in the product. The next EAS reaction is called Friedel-Crafts alkylation, with a primary alkyl halide in the presence of a Lewis acid catalyst like AlX3. In the mechanism, the first part is forming the electrophile, where in this particular example, we're using ethyl chloride with aluminum trichloride. One of the lone pairs on Cl attacks aluminum to form the following electrophile. Then we add this to the benzene ring, where one of the pi bonds attacks the carbon atom connected to chlorine, and then AlCl4- breaks off. This forms the sigma complex, and then one of the Cl aluminum bonds in AlCl4- then deprotonates a hydrogen atom to restore aromaticity in the product. Friedel-Crafts alkylation can also work with secondary or tertiary alkyl halides, but the mechanism to form the electrophile is slightly different. In this example, we're using tert-butyl chloride with aluminum trichloride. One of the lone pairs from Cl attacks aluminum to get the following intermediate, but then AlCl4- dissociates to form a stable tertiary carbocation. This electrophile is then added to benzene to form a sigma complex. Then one of the Cl aluminum bonds in AlCl4- deprotonates a hydrogen atom to then restore aromaticity in the product. And the last EAS reaction is called Friedel-Crafts acylation, where E is an acyl group or a carbonyl group. The mechanism starts with first forming the Friedel-Crafts reagent using thionyl chloride or SOCl2 with a carboxylic acid that contains your desired R group. This forms acyl chloride, which then attacks the aluminum atom in AlCl3. Then one of the lone pairs on oxygen pushes down to form a triple bond, and AlCl4- is broken off to form an acylium ion. Then we're going to add the acylium ion to benzene. One of the pi bonds in benzene attacks the carbon atom, and one of the pi bonds forms a new lone pair on O. Then AlCl4- deprotonates a hydrogen from the sigma complex to restore aromaticity in the new substituted benzene product. So in summary, you learned about 5 different electrophilic aromatic substitutions, or EAS reactions, where an aromatic hydrogen is substituted with an electrophile. The 5 reactions that you learned about were aromatic halogenation with either bromine or chlorine, sulfonation, nitration, Friedel-Crafts alkylation with either a primary, secondary, or tertiary alkyl halide, and lastly, Friedel-Crafts acylation.
Organic.